Continuing with naming, there is another special case we should consider. This is not encountered with all molecules, but it is possible, and that is when we find a molecule that has numbering the same carbon chain length in 2 positions. So, for example, if we number straight across, we have a 6-carbon chain that I'm showing in green. But if we follow the book's numbering in red, this is the correct numbering. And the reason that it is correct is that it gives a less complicated branch point. So it is better to have more branches than to have a branch that has to be put into a parentheses in front of the molecule name. So you want to number if you have 2 chains of the same length in one molecule, you're going to pick the chain that has the greatest number of substituents, the most substituents on the main chain. So I have a second example, and I have numbered this example in red and in black. Now, if we go with the red numbers, then we have this Y branch. So it's the type of branch that has to be put into parentheses. If we pick the black numbers, then that gives us, instead of 1 complicated substituent, 2 simple substituents with no additional branching on either of those 2 substituents. And so the numbering in black is the correct choice for the main chain. Then we can give our substituents as 2-methyl, 3-ethyl, pentane as the main chain. Cycloalkanes. The change that is going to occur with the cycloalkane is that it's going to have a different general formula than other alkanes because there is no terminus with a CH3 group. So if there are no CH3 groups, we have 2 less carbons than a straight chain, 2 less hydrogens than a straight chain. And that means that our general formula for a cyclic alkane is CnH2n. We can write out condensed structures that are cyclic with all of the hydrogens shown, or we can simply draw the polygons that represent the cyclic structure, leaving off drawing the hydrogens, but still knowing that they are there because every carbon must have a total of 4 bonds when it shows 0 net charge. I like the skeletal structure, especially for cyclic structures. To indicate that a chain of carbons is cyclic, we are going to use the prefix cyclo before the main chain carbon number indicator. So for a 3-carbon cyclic structure, we have cyclopropane. For a 4-carbon cyclic structure, cyclobutane, 5 carbons in a cycle, cyclopentane, and 6 carbons in a cycle, cyclohexane. If we have a monosubstituted cyclic alkane, then we do not have to give a carbon number to the carbon containing the substituent. We can simply name the substituent followed by the cyclic alkane. So that gives for the first structure on the left, that's the book example, methyl cyclopentane. The middle book example has a 2-carbon substituent, and it is ethyl cyclohexane. And then the last substituent is unique, and that is because this substituent has more carbons on the substituent than on the ring. Remember, the main chain should have the greatest number of carbons. So because 5 is greater than 4, the main chain is the straight chain portion of the molecule. So this is a pentane. But then what we do with the cyclic structure is that is our branch. That branch is at carbon 1 of the pentane, and it's a cyclobutyl branch. So I have other examples on the slide for you. Let's look first at this 6-carbon chain with a cyclopropane at carbon 2. We would name this 2-cyclopropylhexane. And then at the second structure, the second example that I'm giving you, the longest chain is 2, 3, 4, 5 carbons. You're going to number so that the branch point has the lowest possible carbon. So then our branch is at carbon 1. This carbon branch has a ring that has another substituent, and so this is what we would put this in parentheses because we would call it a branched branch. So we have, for our longest continuous chain, 4 carbons in the ring, which is a cyclobutyl. And if carbon 1 of the cyclobutyl is always the carbon bonded to the main chain, then the substituent on the cyclobutyl is at carbon 3, and that is a 1-carbon group, so it is 3-methyl cyclobutyl. Then you have to put that in parentheses and state that it is at 1-pentane. Disubstituted rings. For disubstituted rings, we are going to number the substituents to give the lowest possible overall numbers, but also to give the lowest possible number to the group that comes alphabetically first. So what I do before I number is I name my substituents. I have a methyl on the ring at 1 carbon, and I have a 3-carbon on the ring, which is a propyl. So because M is before P in the alphabet, I will give the methyl substituent a lower carbon number for numbering my ring. And then I will give the propyl the next lowest carbon number possible. So that this molecule then is 1-methyl 2-propyl cyclopentane. Looking at the middle example on the slide, we have a 1-carbon branch and a 2-carbon branch. So we have a methyl and an ethyl. Ethyl is alphabetically first, so I will call it carbon 1. And then I will label the methyl carbon at the next lowest possible number, which is carbon 3. Okay. So that this is 1-ethyl 3-methyl cyclopentane. If we look at the example on the far right, we have 2 1-carbon branches. So we have 2 methyls. So in this case, it will not matter which is carbon 1 and which is carbon 3. It could be either way because they are alphabetically equivalent. So this is 1,3-dimethylcyclohexane. When we have two substituents with the same lowest number, we want to make sure we have the lowest number overall for all substituents. So, for the first molecule, we have one carbon that has one C, and then we have a ring carbon that has 2 times 1 C. So in this case, when I'm numbering, if I start at the carbon that only contains 1 C, then I have 1, 2, 2 for my numbers. If I start at the carbon that has 2 carbons, 2 1-carbon groups, then I have 1, 1, 2. 1, 1, 2 gives us the lowest overall number. It adds to 4. The other numbering option adds to 5. And 4 is less than 5, so I am confident that 1, 1, 2 is the correct numbering option. We will often have 3 substituents on a ring where 2 of the substituents are immediately next to each other and the third substituent is there is a non-substituted carbon between. When you are numbering a molecule like this, you always want to start at the carbons that are adjacent. So you're going to start numbering from adjacent carbons toward the carbon that is separated, so that the carbon that is separated has the lowest possible number. And all carbons have the lowest possible number. So if we do start from the carbons that are adjacent, then we get 1, 2, 3, 4 with substituents at 1, 2, and 4. If we had started from the carbon that was separated instead of the carbons that are adjacent, then we would have gotten 1, 3, 4, which is incorrect. So 4, 2, 1 adds to 7. 1, 3, 4 adds to 8, and 5, 1, 2 adds to 8. And the first answer given is the correct answer. So we're going to move away from naming molecules that have only carbon and hydrogen to naming molecules that contain halogens and oxygens and nitrogens in addition to carbon and hydrogen. And that is going to require us to understand what we call functional group priority. So as functional group priority changes, the suffix of the name will be changed so that the functional group that is said to have a higher priority will have the suffix, and the lower priority functional group will be represented by a prefix. So for example, an alkane, which contains only carbon and hydrogen, has a lower priority than a molecule that has an alcohol. So if we have a molecule that contains carbons, hydrogens, and an OH group, then the suffix of that molecule will be -al. And the alkane portion of the molecule will be represented in number of carbons, and any branches will be represented as alkyl groups. And we're going to go through this. Alcohols are probably the highest functional group that we're going to consider in this chapter. We're also going to look at amines and ethers, but ethers and alkyl halides will never change the suffix. They will always be represented as a prefix. So, classification, let's start with alkyl halides, and we're also going to have to, for all of these molecules, be able to define carbons bonded to halogens, oxygens, and nitrogens as being primary, secondary, or tertiary. Well, alkyl halides, the designation of the halide depends on the designation of the carbon it is bonded to. So a primary halide is bonded to a carbon that is only bonded to one other carbon. So a primary halide is bonded to a primary carbon. A secondary halide is bonded to a secondary carbon, a carbon that is bonded to two other carbons. And a tertiary halide is a halide bonded to a carbon that has 3 bonds to other carbon atoms. Nomenclature of halides. The suffix does not change. We still have anes, so we want to find the longest possible chain to get the suffix. In the example on the top left, we have a hexane. And then we name our substituents. So we have a substituent of bromine at carbon 2 and a substituent of methyl at carbon 4, and that gives us 2-bromo-4-methyl, writing them alphabetically. The substituent in the top middle, we have a 7-carbon chain with substituents at carbon 1 and carbon 6. We have a chlorine at carbon 1, and at carbon 6, 2 methyl groups, so that is 6-dimethyl, or 6,6-dimethyl. And then the length of the chain, heptane. When we have a cyclic structure with an halogen bonded to it, we still do the same rules where the numbering is dependent on the alphabetical order of the substituents. So we have a 2-carbon fragment, which is ethyl. And then we have the iodo group. So that when we name this, because ethyl is alphabetically first, it will be carbon 1, and iodo will be carbon 2, and then you can continue numbering the chain if you prefer. So that this would be 1-ethyl 2-iodo cyclopentane. On the example at the bottom left, we have a cyclic alkane as our longest chain of 5 carbons, and it has a branch. A branch is any carbon that is not a ring carbon, which is branched. So the branch has a branch. It has a bromo on carbon 1 of the branch. So we have to put this in parentheses and say that the longest carbon chain in the branch is 2C, which is ethyl. And that at carbon 1 of this branch, there is a bromo. So this would be parentheses 1-bromo-ethyl, close parentheses, cyclopentane. Then if you look at the book's example at the bottom right, we have a ring with 3 substituents. And I'm going to start numbering from the substituents that are adjacent towards the substituent that is separated to give the lowest possible number. So I have 1, 2, 3, 4. And so I have 1 carbon at carbon 1, chloro at carbon 2, and a bromo at carbon 4. If I list these in alphabetical order, I will get 4 bromo, 2 chloro, 1 methyl cyclohexane. I have drawn another example at the bottom. It is a 6-carbon ring with substituent of ethyl and bromo. And bromo is alphabetically before chloro, so I will say that the bromo carbon is carbon 1. And then no matter which direction I label from that carbon 1, the other substituent is at carbon 4. So in that case, it doesn't matter which direction that I go, I will get 4 for the second substituent either way. So that would give me 1 bromo 4 ethyl cyclohexane.